So the lecture might seem a little segmented at this point. That's because I am recording the last part separately. As some of you I may have already told, I did not hit the record button after we watched that little video of the P4 reacting with the Cl2. Anyway, so we could look at this equation. Okay, and you guys actually did this lab last week. Not last week because you took a test last week, but the week before you did this lab on Thursday where you had solid magnesium. You burned it and it combined with gaseous oxygen from the air to form magnesium oxide. So this actually, we could do a check, and this is definitely balanced. So here we go. We do our little brick wall and do a tally of magnesium and oxygen on either side. So magnesium's over here, 2, oxygen's over here, 2, magnesium's over here are 2. Okay, that applies to the whole thing. And oxygen's over here also 2. So yes, it's definitely balanced. It's balanced using these stoichiometric coefficients of 2. There's an implied stoichiometric coefficient of 1 in front of the O2 and 2. So 2, 1, and 2 respectively. That does balance the equation. So I'm not going to play this for you, but this actually is what you guys did in your little crucibles. Last week you burned magnesium to form magnesium oxide. So when we come up with that set of stoichiometric coefficients in front of the reactants and the products to go ahead and balance the number of atoms of each type of element on either side of the reaction arrow to get the same number of atoms of each element, that is actually just a conservation of matter. Okay, conservation of mass, conservation of matter. In the ordinary chemical reactions that we're dealing with, all of the atoms, for instance, of hydrogen you begin with need to will appear as hydrogen in the product side. We aren't doing any sort of nuclear chemistry where you are getting different elements, atoms of different elements. So there are different ways to come up with that set of stoichiometric coefficients, and the one way I want to emphasize is something called by trial and error, otherwise known as balancing, coming up with a set of coefficients by inspection. So here's my little hint: use a pencil, because what you're going to see is you're going to see that actually you're going to kind of go back and forth between reactant and product side, and you will be upgrading your coefficients sometimes to make sure that you get what you need, the same number of atoms of each type of element on both sides of the reaction arrow. So my first hint is a big one. Okay, thou shalt not create new compounds. Thou shalt only use the reactants and the products that are specified in the unbalanced chemical equation. So if you change the subscripts, so for instance, if I had H2O as one of my reactants or products, and I'm like, hey, dude, if I go ahead and put a 2 here, then it's balanced. Okay, you cannot do that. Okay, actually, that's a different molecule. That was hydrogen peroxide versus a water molecule. So you can't change the subscripts, but you can change the stoichiometric coefficients. So we're going to do an example here, a couple examples, what that looks like. Okay, so you can change the stoichiometric coefficient. Sometimes I say the coefficient is kind of like the big number to the left of the species. So when as you change stoichiometric coefficients during your balancing process, just keep in mind that that coefficient, that big number to the left of the species, actually applies to the entire formula. And I'll kind of show you what I mean coming up here. So let's go ahead and do this one by inspection. Let's draw our brick wall, separating reactants from products, and go ahead and start a tally. I think we'll try it this way. So we have Fe we need to account for, we have hydrogen we need to account for, and we have oxygen we need to account for. I'm going to kind of draw it straight through like this, kind of extend my brick wall, okay, and kind of make a partition there. So when we start out, if we go with coefficients of 1 across the board, can you see on the reactant side I have 1 iron, 2 hydrogens, and 1 oxygen. On the product side, it looks like I have 3 irons, 2 hydrogens, and 4 oxygens. Okay, so I have a slide coming up that says this, but basically we want to use anything that appears in its uncombined, which means there are no other elements associated with it, uncombined elemental form. So actually we have iron is in its uncombined elemental form, and hydrogen is in its uncombined elemental form. So I'm going to put weight here. So actually I am going to kind of hold back in putting the coefficients in front of the iron and the H2 until kind of the end. So with that in mind, let's go ahead and plug away. If we go ahead and let's say we want to fix our hydrogens first. Okay, let's go for our hydrogens. Okay, notice I have 2 hydrogens on both sides. Well, that didn't help. Let's go ahead now and go to our oxygens. Okay, on our oxygens, okay, notice that on the reactant side I have 1, and on the product side I have 4. So I need to up the reactant side to 4. So I can get 4 oxygens if I go ahead and put a 4 here in front of my H2O. So then I can update that. So the number of oxygens is 4, which is great. But now I monkeyed with my number of hydrogens. So hydrogens now is not 2, but it's 8. Okay, so if I'm kind of keeping tabs here, it looks like, for now anyway, my oxygens are balanced. My hydrogens are not balanced, and of course my irons are not balanced. Alright, so let's go for our hydrogens next. Okay, I know I said to leave hydrogen, weight for hydrogen, but between hydrogen and iron, hydrogen is even, iron is even less complicated than hydrogen. So if I want to fix this over here, this 2, okay, I need to get 8. So the way I get 8 out of H2 is I put a 4 in front of H2. So if I put a 4 there, then I need to update this to 8. And ta-da! Now my hydrogens match. Last but not least, let's go ahead and fix our irons. So here we have iron on the product side of 3, and we have only 1 iron over there on the reactant side. So I can get 3 irons on the reactant side if I go ahead and put a 3 in front of the Fe. So we would say the coefficients of 3, 4, and there's an implied 1 there, and 4. Actually, that is a set of coefficients that balance this. Oops, I didn't update my iron, did I? That changes that to 3. Now they're all balanced. So there we go. Coefficients of 3, 4, 1, and 4 across the board. It's kind of like a recipe. Okay, it means in order for this reaction to occur, basically you're going to have 3 Fe's, 4 H2O's, going to form 1 Fe3O4 and 4 H2's. It is indeed balanced. All right. Now, this next one actually is an example of something we haven't necessarily talked about yet in this class, but we will get to ions, and we'll get to ions that are what we call polyatomic ions. And I mention that because this one actually has a set of SO4, actually it's SO4 2-, but the SO4 stays as SO4, so I'm going to treat it as a unit. The other unit up there is the OH. It stays as a unit. Okay, on both the reactant and the product side. So when I go ahead and do my tally here, here's my brick wall. The things that I need to balance, I'm going to keep those together. So things I need to balance include aluminum, SO4, and it's SO4 2-, but I'm just going to leave SO4 for now, Na, and OH. Okay, so those are the things we need to balance between the reactant and the product side. This is what we call an exchange reaction. Okay, so starting out, it looks like I have 2 aluminums. I have 3 SO4s, or 3 sulfates. I have 1 sodium and I have one OH minus or hydroxide group on the reactant side. On the product side, I have one aluminum, I have one sulfate, I have two sodiums, and I have three OH minuses or hydroxides, OHs. Alright, so I don't see anything glaring to wait until the end, so let's just go ahead and kind of plug our way, start at the beginning here. So if I go ahead and want to balance my aluminums first, okay, I notice that I need to put a 2 here to get my 2 aluminums. Let's go ahead and update aluminum. That will give me 2 aluminums, but now that gives me what? 6 hydroxides. So here we go, better update that one too. Okay, so we're on our way. Let's go ahead and fix the sulfates next. Notice that on the reactant side I have 3 sulfates and I only have 1 sulfate on the product side. So I can get 3 sulfates if I put a 3 there. So let's go ahead and update. That means I have 3 sulfates. Okay, but that means I have 3 times 2 or 6 sodiums. So I better update my sodiums. So I'm going to put a 6 there. Alright, so if you're keeping track, our first 2 things, for now anyway, because sometimes they go out of balance when you're trying to kind of fix something else. So now aluminums and sulfates look fine. For sodiums, notice that I have 6 sodiums here on the product side, and so to get 6 sodiums on the reactant side, I of course need to put a 6 here. Let's go ahead and update that as 6 sodiums, and now the other thing I now have are 6 OHs or OH minuses, 6 hydroxides. So by my count then, actually, that finished. Now we have a balance of everything. Everything is balanced. Okay, so actually that is, that set of coefficients correctly balances that equation for that reaction. So while I'm here, let me go ahead and mention something that is helpful at times. So do you see where, like, if I wanted to scale this thing up, I want to scale it up. It's kind of like scaling up a recipe, scaling up making brownies. So for instance, instead of 2 AlOH3s, I say I wanted 4. Okay, so I take 2 times 2 to get 4. So actually then, do you see where that means that this would scale up 3 times 2 or 6, and this would scale up 6 times 2 or 12, and this would scale up 1 times 2 or 2. Okay, this that I have down here, these numbers, this set, okay, is actually an alternate set of stoichiometric coefficients that work equally well for balancing the same chemical equation. Okay. So yes, it is balanced, and you could, if you didn't recognize the whole SO4 2 minus, the sulfate, and the OH minus, you actually could still balance it for sulfurs, oxygen, and hydrogens, and it would work the same way. Okay, so like I was saying, keep the thing that is in its uncombined elemental form till last. So let's do another example, and this one is actually a good example to get under our belt because you'll just see. The problem with this reaction is that actually, as you see, oxygen is over here on the reactant side. Oxygen on the product side actually exists in 2 locations, both the carbon dioxide and the water. So we're going to have to take that into consideration as we work the problem. So let's see, we need to account for carbon and hydrogen and oxygen. Here's our tally-ho. Alright. So it looks like right off the bat we have 4 carbons and we have 10 hydrogens and we have 2 oxygens if we go with stoichiometric coefficients of 1. With regard to carbon on the product side, we have 1 carbon. And now, be careful, because now for, well, not be careful yet. For hydrogens, we have 2 hydrogens. Here's where you need to be careful. Notice if we go with coefficients of 1 and 1 over here, okay, we have the number of oxygens, we have 2 plus 1. We have 3 oxygens. So we have to count oxygens in both the carbon dioxide and the water. All right. So the thing we're going to hold back actually is the O2. So I'm going to circle O2 and I'm going to say wait. And what I mean is I'm going to wait for that number that right there, that coefficient from the O2. So let's go ahead and just start at the top and let's fix our carbons. Of course, I have 4 carbons on the reactant side and only 1 carbon on the product side. So I can get 4 carbons, or to get 4 carbons, I'll put a 4 in front of the CO2. Now let's update our carbons. Now we have 4 carbons as we needed, but now let's see, oxygens. We have 4 times 2 or 8 plus 1. We actually have 9 now oxygens. Change that 3 to a 9. Okay. So far so good. Okay, so our carbons, we might need to revisit it, but so far our carbons are balanced. Now let's look to our hydrogens. The hydrogen, notice that I have a whopping 10 on the reactant side. So to get 10 on the product side, if I put a 5 in front of the H2O, that does give me 10 H's, and it gives me 5 O's. So let's go ahead and update that. Instead of a 2, now I've got 10, which is what I was after. But now my oxygen changed, so I have actually 5 oxygens there, plus, what do we say, 8 oxygens over here. So 5 plus 8 is 13. So I have a whopping 13 oxygens now. Okay? So, alright, carbons are good, hydrogens are good. Oxygen, not quite, not yet. Okay? So here's a deal actually where we have kind of what I call the odds and evens problem. Because notice that we need 13, okay, over here on the reactant side because we have 13 on the product side. The problem is that these 13 that we need are going to come in twosies, okay? They're going to come in pairs from O2. So now I'm going to introduce something called a fractional coefficient, okay? But in order to, the way I think of fractional coefficients when it comes to O2 specifically, fractional coefficients work well for things like diatomic elements, so, or triatomic elements. Okay, something that you can actually split. So this is an O2 molecule, okay? So this is one O2 molecule. Can you see where if I have a half of an O2, that is just one oxygen atom? Okay, that's kind of, if you break this in half, then you just have one. So kind of along those lines, if I go for, up here, this coefficient in front of the O2, if I go 13 halves, or if I go 6.5, 6.5 O2 molecules, can you see where that gives me the 13 that I need? It surely does. So actually, if I go with either 6.5 or 13 halves in front of the O2, okay, that means with regard to oxygen atoms, I end up with 13, okay, which, voila, 13 is what I needed to equal my other side, okay. Now, you really can't, when you're combusting something or when you're reacting anything with oxygen, it's in its molecular form. It's not, you can't break that chemical bond between the 2 oxygen atoms, okay? But a fractional coefficient is okay if you think in terms of relative moles of molecules, and we'll be talking more about that in our lecture on Friday. So here we go. Yep, that is a perfectly legitimate way of set of stoichiometric coefficients. Across the board, we have 1 in front of the C4H10. Okay, 1 here, 13 halves, 4, and 5. That's a great set of stoichiometric coefficients. You have to be thinking of them in terms of moles of molecules, but that's great. Now, alternatively, if this half just drives you nuts, okay, which sometimes it does me, we can actually we can scale it up, multiply everything by 2. We need to multiply everything by 2, and that 13 halves will become 13. 1 in front of the C4H10 will become 2. And then, of course, we have 8 CO2s and 10 H2Os. So these are both perfectly balanced equations, okay, for the same chemical reaction. So we can do a mass balance or a balance for the non-fractional stoichiometric coefficient, 13, and here we have it looking at it with the fractional coefficient. So again, fractional coefficients are okay as long as you're not actually breaking any chemical bonds. No chemical bonds were harmed using this fractional coefficient, as long as we think of them in terms of moles of compound or molecules. So we'll be talking more about stoichiometry. It doesn't look like a good definition to put on a test, but in general, stoichiometry is when you have the known quantities that of reactants and products. You know how they are going to react based upon the chemistry. Based upon the unbalanced chemical equation, you have balanced it. Okay, relative amounts are known. So, as I said, here is your the problem assignment, and I did not give any hints for these. I'm kind of reserving hints for down the road when there's kind of multiple steps to show you. But remember, I did show you that website and encourage you to go there, even though you can actually get all the answers to these without having to work them. But it's a great website for other things too.